Well, I want to talk about level surfaces of a function of three variables and talk about gradient at level surfaces. So I'm going to give you an example. Let's assume f of x and y and z, three variables, is equal to e to the power negative parentheses x squared plus y squared plus z squared. And find the level surface of this. We know we have to, for level surfaces, we put the output equal to constant, and then we solve for, and we figure out what's level surface that is. And so we get this, and if I take the natural log, multiply by negative sign, I get x squared plus y squared plus z squared equal to negative c. And it makes sense because c was basically less than 1, and therefore the negative natural log of c is going to be a positive value. So basically the level surfaces are going to be the spheres. And so you can see a bunch of spheres. Now I want to find the gradient of this function. So gradient of f is going to be basically equal to partial of f with respect to x, which is going to end up to be negative 2x and e to the power. I'm going to show that because x squared plus y squared plus z squared also is called r. I'm going to use r in r squared. I'm going to use r squared. So e to the power negative r squared. And then the partial respect to y is going to be negative 2y e to the power negative r squared. And partial respect to c, it's going to be negative 2z e to the power negative r squared. And therefore, you can see that basically the gradient of f, which points to it actually points to greatest rate of change, is basically pointing radially inward. And you can actually see that from the fact that it's equal to negative 2 e to the power negative r squared times x, y, and z. X, y, and z is radially outward, and then this is multiplied by negative sign, therefore it's radially inward. And so basically, and this is the shape that you see. Now, if this was, the function was something that you would get level surfaces that were sphere, and the direction was radially outward, then the gradient vectors at any point would look outward. Versus here, you can see that the gradient vectors are looking inward. So depends on the function, and even if you have a bunch of spheres for level surfaces, you may have inward or outward, or basically different lengths of the gradients every time. So you can see the length of the gradients in here. Successfully or not, but or maybe the other way around. And you can see the length of the gradient and the normal to the surface.